Welcome to Hydrocarbons Part 2. In this video lecture, we are going to introduce the idea of isomers with organic compounds. Let's get started. And now, at the simplest level, here are the isomers. We will expand on this a bit in a future video, but this is a great foundation. So we're going to look at really three primary types of isomers in this video. The first one is called constitutional or structural. And I've written the definitions down here for you below, right? So here's structural isomers. So it's compounds that have the same chemical formula but different connectivity, right? So an example here would be like if we had C5H10, right? So there's the same chemical formula, but we could put those 5 carbons in a straight chain, or we could do 4 carbons with a branch, or we could do 3 carbons with a branch, right? Or let's look at, oh, whoops, I'm sorry, that's C5H12. That's all right. Okay, now let's jump to C5H10. Now for C5H10, here, C5H12, these students tend to, these make sense. Okay, we have our 5 carbons and carbon wants 4 bonds, so we just can put it together in a lot of different ways. Here's C5H10. Here we have a straight chain with a double bond, right? Or we could put the double bond here, and even that makes sense. But here's the crazy one. Or we could actually have a ring. All 3 of these compounds are C5H10. They have the same chemical formula, but they definitely have different connections. So we have a couple different examples of structural or constitutional isomers. Now, let's look at conformational isomers. Now, these are 2 different types of stereoisomerism. And with stereoisomers, right, now we have the same chemical formula and the same connections. All right, but, whoops, okay, but we have different spatial arrangement. Whoops, right, so same chemical formula and same connections, but different spatial orientation. All right, so there's 3 different types of stereoisomers. We're going to just focus on 2 for this video. And the first one are conformational. This is all about rotation. All right, so when we look at conformers, here's our definition right here for conformers, right? They're actually the same compound with different rotations. So we could have, right, so there's our C5H12, and now if we focus, for example, right here, we could rotate, right? So there is still C5H12 and it's still pentane, but these would be considered conformers. So now I want to, I'm going to show you a simplified model here. So let's look at these models. All right, so oops, there we go. Okay, so here we have, right, they're both C5, right? Now to change them, right, I just rotate, let's see, how do I want to do this? Yeah, this will work. Okay, so now if I rotate here, right, woo, there we go. Okay, no, I had it right. There we have the same, right, we have the same compound, right? We just rotated, right, and we could go this way. And now they're back to being the sawtooth, all right? So these are conformers. So right now, they would be considered identical. If we rotate one of these, now they're considered conformers. So they are the same compound, but when they have different rotations, the best term to describe them is conformer. And here I've just focused the models on the carbons only to make it not so busy, right? So when we have the same compound in different rotations, the most correct term would be conformers. And now the other type of stereoisomer we're going to look at is geometric. And here, these also come in pairs, and we have cis and trans. All right? So when you think cis, think same side. And with trans, think like if we had a transatlantic voyage, we would be going across the Atlantic Ocean. We would say across the sides. So geometric isomers only occur for two types of organic compounds, and that would be when we have a double bond, right? So if we look here, right, if we think about the double bond kind of as a plane, right? So here we see that these carbons are on the same side, so it's cis. Here, right, one's here, and we would have to go across to the double bond to get to the other one, so it's trans. All right, so let's look at these briefly. Right, and so let's put them, we'll do them this way. All right, so here we see, right, in this hand we see how the double bond and the green atoms are on the same side, and then here they're across the double bond, and now there's no rotation. I can't twist this to make the other one. We can't, it's not like conformers where we could twist them and make them into each other. These are unique compounds, and we'll look a little closer at that on the next page. There's one more way that we can make geometric isomers, and this is with rings with two substituents, right? Substituents is a fancy way to say branches, all right? So we could have our six-membered ring, and we could have both branches, right, a wedge, right, both branches going up. And so this would be another example of cis, they're on the same side. Or we could have one of our branches going up and the other one going down. And so that would be trans. All right, so let's look at those models. All right, so here, up or down, right? Here's the two, right? They're both up. So you could see, so here's our ring. So we have the plane of the ring. And so, woo, there we go, right? They're both on the top. So that would be cis. And then if we compare that with this model here, now we see that one is going down and one is going up. So with the plane of the ring, they're across that plane of the ring, so that's trans. So that's our two examples of geometric isomers for cis and trans. And those are right here, right? And so that's doing with the difference in spatial arrangement. Alrighty. Okay, let's move on to the next page and look a little more closely at the SIS Trans Isomers, the geometric isomers. It's very important to realize that they cannot interconvert. They are unique compounds, right? So here we see the dash and the wedge. So that would give us our trans. And then here, there's two wedges. So that's why it's cis. Okay, so that's an important part of the name. And then with the alkenes, think about the plane of the double bond. So here, right, we have them on opposite sides. The substitutions are on the opposite side of the double bond. So that's why we have trans. And then here, they're on the same side. So cis, and then I included a little bit of information here, right? See, they are different compounds. The melting points are different. The boiling points are different. They can have differences in water solubility, all different kinds of things. One thing to notice, though, especially with the double bonds, is that it's important that there's two different groups, right? So if we look at this compound right here, all right, there's no cis trans. All right, because when we look at the carbons forming the carbon-carbon double bond, notice that these two groups are the same, right? So here, right, we have those hidden hydrogens that we don't see. So we have our methyl group and our hydrogen, and our methyl group and our hydrogen, right? So we have two different groups. So it's possible to have cis trans. So in the same way that I mentioned that with rings, the rings can only have two substituents. So not all rings can have cis trans isomers. The same thing with double bonds. Not all compounds with double bonds can be cis trans. And so why do we care about this? Well, it's pretty trippy. Right now, the fact that you can even see this video is taking advantage of the interconversion of cis trans isomers. This rhodopsin is a compound that's part of our vision, and right here we can see that there's a cis double bond, and when the light energy, right, the image that we want to see brings in light energy, there's a chemical reaction that converts this double bond to a trans double bond, and through that rotation it triggers the nerve impulse. And that gives us vision. So cis trans isomers are an important aspect of chemistry, and they're helping us learn more about it. All right, so we have a lot of information here. Let's practice it to make sure that we know how to apply this knowledge. So let's look here, right? So let's go back through, right? So you got to know the term structural isomer, right? Same chemical formula, different connections. So right now would be a great time to pause the video and see how well you can do at drawing the 5 structural isomers for C6H14. All right, let's see how you did. For me, I like to start with the straight chain. So there's 2, 4, 5, 6, okay? So there's our 6 carbons. And then basically just start shortening the chain. So we'll take this first carbon off and put it as a branch. And then we had a couple options. It could go to this inner carbon or that inner carbon. So that gives us 2 more possibilities. Sometimes we can get carried away and try to keep going, but then we would just have the identical compound flipped like a pancake. So we started with a 6 carbon chain, and then here's our 5 carbon chain. Now we can go to a 4 carbon chain, and that would leave us with 2 branches. So those 2 branches could go on the same carbon, or they could go to 2 separate inner carbons. So these would be the 5 structural constitutional isomers for C6H14. Alrighty, now let's work on the next topic. So this would be another good time to pause. What are the relationships between compounds A, B, and C? Alrighty, so the first thing we want to do is double check our carbon count. And so we see carbon 1 has 6 carbons. And so does compound B, right? A and B both have 6. And so does C. All right, so now we have the same all 3 have the same chemical formula. But what we notice about A and B, right, is they're actually the same compound. There are 6 carbons in a row. We just have this difference in rotation. So we would describe these as conformers, right? The same compound, but shown with different rotation. And this can be helpful when you're working in groups or working with someone studying outside of class. Sometimes people will draw the same compound but do different conformers, And I don't want that to cause you any headaches or frustration. Just go, oh yeah, we just showed different rotations. They're the same compound. But here, C is definitely different, has different connectivity. This 6th carbon is a branch. It's not part of the main chain. So the relationship between A and B and C would be structural or constitutional isomers. Alrighty, now let's see if we can put all of this together. So now we have, here is our reference compound, compound 1, and we have 6 compounds to compare, 2 through 7. So the idea here, we would look at 1 and 2 and say, what's the best description of their relationship? And then ask that question 5 more times. So this would also be a great place to pause the video for a moment and see how well you do, and then we can check your work. Okay, let's see how you did. So when we look at the reference compound, we notice that we have 2 wedges and they're coming off of carbon 1 and carbon 3. All right, so this would be cis 1, 3 dimethyl cyclopentane. And when in doubt, name it. Write out the name. That can also help. All right, so let's compare with compound 2, right? 1, 2, 3, 4, 5. So we still, right? We still have 1,3 substitution, but now notice it's trans. Okay, so everything's the same except we have cis and trans. So this would be a geometric isomer. Let's try compound 1 and 3. We still have the same chemical formula, but notice now both branches are coming off of the same compound, right? We have different structures. So this would be structural isomer. Same chemical formula, but different connectivity. Let's look at compound 4. Now this one, right, it's rotated, but that's where we use our brain yoga. Right, and we see that it's still, right, 1,3 dimethyl, except it's trans. So this would be a geometric isomer compared to compound 1. Alrighty, let's keep going here. Compound 5, we go 1, 2, 3, 4, 5. So if we look quickly, we're like, oh, look, it's cis. And it's true that it's cis, but it's cis 1, 2, not 1, 3. So these would be structural isomers. Same chemical formula, but different connectivity. A 1,2 substitution versus a 1,3. Alrighty. Let's look at compound 6. 1, 2, 3, 4, 5. Aha! So same chemical formula, same connectivity, but we're back to that trans. So another example of a geometric isomer. And then last but not least, we have compound 7, and we look here. 1, 2, 3, 4, 5. And so this is, they're both cis. So cis 1, 3 dimethyl cyclopentane. Okay, so this one's identical, right? It's just been, right, just rotated in the plane of the paper. Alrighty. Okay, so we're going to have a little bit more practice. So isomers tends to be a very challenging subject. And so I want to give you a lot of guided practice so we can build your confidence so you're ready to work independently. So this will be our last page of practice. This would be another good opportunity to pause. So I'll just pause here once and give you a chance to answer these questions and then restart the video, and then we'll work through the rest of them together. All right, let's see how you did. Okay, so if we look at A through E, and we start counting the carbons. Okay, 6 there, 6 there, another 6, another 6 there as well. Okay, so all of these compounds are C6H14. They all have the same chemical formula. All right, so which ones are structural isomers? Well, now we want to look. So we notice here that A is the only one that's a pure straight chain. So it stands alone. If we look at B and C, we see that they both have a 5-carbon chain with a methyl group coming off of carbon 2. All right, so these are also, these two are the same compound. And now if we look at D, now we see we only have a 4-carbon chain, and then there are 2 branches coming off of the second carbon. So this is a unique compound. And last but not least, we look at compound E, and it also has a 5-carbon chain, but notice now that the branch is coming off of carbon 3. All right, so amongst these 5 compounds, we have 4 unique compounds. So we would say that A is a structural isomer with B and C, and with D, and with E, right? So these are, as I've boxed them, these would be the structural isomer groups. And then we only have one conformer. Here when we have B and C, we notice that around carbon 4, we have a rotation. All right, don't get confused by the pancake flip. If we rotate, I'm going to rotate this back so you can see it. Okay, so this would be B and C. So notice, right, that it's just the rotation right here. So B and C are the conformers, right? All right, and then for cis and trans, making sure that we know when these terms apply. So a ring with only 2 groups and 2 wedges, that's going to be cis. Here we have a double bond. We draw in the plane. When we look at these 2 carbons, they have, right, a methyl group and a hydrogen, an ethyl group and a hydrogen. So this is eligible for cis trans, and we see that the groups are across the double bond. So that's trans. Trans can be a little tricky when we draw it in the sawtooth, right? When we're first introducing it, we showed it like this, right? So it looks a little easier to see. But normally when we see it written, it will be written like this. So you just gotta, you know, do a little brain yoga. All right, how about here? Right? There are 2 substitutions, but notice they're coming off of the same carbon. So this is not applicable. There is no cis trans here. This one's pretty tricky, right? So we have this group and this group on the same side. So this double bond would be cis. But now if we look at the second double bond, they're across. So we have one cis double bond and one trans double bond. That's about as tricky as we'll get. And then let's look here. Here's our double bond. But notice, right, we have the same groups. So this does not meet our criteria for cis trans. And the same thing, here's a double bond, but with the ring, cis and trans is not applicable there as well. Alrighty, okay, so that wraps up our introduction to isomers. This is a very challenging section, but it's very important because it's going to have great impact on biochemistry. So this would be a great time to work those post-video practice problems to reinforce your understanding.